Good morning, children, and welcome to physics class. So, this year you are going to have theory and practicals. I know this is your first class, so I'm just telling you what are the chapters included this year for physics. All right, so you will be having theory, practicals, and activities. All right. So in theory chapters you have unit 1. In unit 1 you have physical world and chapter 2 physical world and measurement. In physical world and measurement you have chapter 1, that is physical world, chapter 2 units and measurements. In unit 2 you have kinematics, which includes chapter 3 and 4, motion in a straight line and motion in a plane. In unit 3 you have laws of motion, that is chapter 5. Unit 4 you have work, energy and power, that is chapter 6. Then unit 5 you have motion of system of particles and rigid body. So you will be studying in chapter 7 the system of particles and rotational motion. Then in unit 6 you have gravitation, that is chapter 8 gravitation. Under unit 7 you have properties of bulk matter, which includes chapter 9, chapter 10 and chapter 11. Alright, so chapter 9 is mechanical properties of solids, thereby chapter 10 is fluids and chapter 11 is thermal properties of matter. In unit 8 you have thermodynamics and that is chapter 12 thermodynamics. In unit 9 you have behavior of perfect gases, which is under kinetic theory. And then unit 10 you have oscillations and waves, which include chapter 14 and 15. So these are some of the chapters included for theory, and you will be having them for 70 marks in your final exam, all these chapters. Thereby we have section A practicals and section B practicals, that is experiments, which we are going to carry forward very shortly, and also you will be having activities. Alright, so about all of this I'll just brief you. So we have to write at least 12 to 15 experiments, so 6 to 8 activities, alright, and also a project report has to be carried on by all. So you can do a project, a hands-on project on any topic of your choice of physics, which will be evaluated in the end. Alright, so your practical records will carry 30 marks, in which the experiments, your practical record, your activity and your investigatory project will all be included in these 30 marks. So 70 and 30, which is 100 marks for your final exam. Alright, so the books which the NCERT has prescribed is Physics Class 11 part 1 and part 2. So you have two books here. You have part 1 and part 2. It is published by NCERT, and also if you want to refer lab manual, you can also go to Laboratory Manual of Physics for class 11 published by NCERT. If you actually want to know more about the concepts, you can always refer H.C. Verma, that is Concept of Physics. Then you can also refer Dinesh Publications, which is New Millennium Physics. And you can also refer D.C. Pandey, that is Understanding Physics. So these 3 reference books I will also be referring. If in case you want to refer more than what I teach, you can always go ahead and refer it. Yes. So with this brief introduction about your chapters and your course structure, let us get going to the first unit in your 11th standard physics, that is physical world and measurement. Alright, so this is chapter number 1. We are going to study about physical world. Yes, so what are the things that you will learn from this chapter? First thing is, you will know what is this physics about. How did physics come into existence? What is the history behind it? How wonderfully crafted is physics in the stream of science? Then you will be able to identify science in various aspects. Where do you apply science? Then how to apply scientific method in various situations. What is scientific method? How we go ahead in science, right? To know more about the scope and excitement about the subject. So where does physics have scope, and what is the excitement about this physics subject? Then you find the relationship between physics and society. Is it applied in our surroundings? Yes. Then you will also be able to understand about the fundamental forces in nature. What are the fundamental forces in nature? You will be able to understand by this chapter. Yes. So you've been studying science throughout grade 10, right? So as you have chosen this mainstream of science, what is science? Science is a systematic enterprise or study that builds and organizes knowledge in the form of testable explanations, predictions about the universe, rational explanation, and reliable application. Okay, so it is a very systematic study that builds brick by brick by brick, and it organizes the knowledge. Whatever knowledge we have, it organizes in a systematic manner. Okay, it uses a lot of testing techniques. It uses a lot of predictions of the universe, the earlier theories, laws, right? Rational explanations. It requires explanation. You cannot tell it is science until and unless proven by facts, right? And it's reliable application. So once it's a fact, then application becomes very easy. So science means nothing but to know a particular thing. Latin verb scientica means to know. The Sanskrit word Vignan and Arabic word convey similar meaning, called as knowledge. So you have various contributions of various countries across. So early civilizations of Egypt, India, Chinese, Greece and Mesopotamia and many other countries have contributed in the significant application and theory of science and physics. So the science has a lot of branches, right? It has physical science, it has life science, it has earth science, you have mathematics, right? In physical science, you have physics and chemistry. In physics, again, you have kinetics, mechanics, electromagnetics, thermodynamics. In chemistry, you have inorganic chemistry, electrochemistry, and analytical chemistry. In biology, you have botany and zoology. In earth science, you have geology, meteorology, and astronomy, right? So science has various branches. Okay, and physics is related to various branches in science, right? So physics is related in maths, so maths is the king of physics and physics is the queen of math, right? So physics and maths play a very important role. They are interdependent on each other. So learning physics is just like learning math, all right? So but in application of math we say it, right? Then as physics is also related to astronomy, right? The cosmic structure, then all the components in the universe, how they behave is related to physics. Then physics and chemistry, right? The Avogadro numbers, the molecules, behavior of molecules, everything. Then chemical physics, right? So all these are different applications, how physics is related to other branches of science and how the science has branched into various components. Physics is one of the main branch in science. So what is physics? It's a way of describing the physical world, right? Physical world in the sense everything. Whenever you see something, it is, it may be matter and time, it may be space and time, it may be matter and energy, right? So physics comes from the Greek physis, means nature. What is the nature of that particular thing? How does it behave? How it functions physically, what it does, how, right? So all that comes under physics. That means it describes the natural things, the natural phenomena that is occurring in certain things. The branch of science concerned with the nature and properties of matter and energy. What is the nature of this matter? What is the nature of this energy? How is energy produced? All that is nothing but physics, right? So how it physically functions. So physics, see, every other field may describe what is this, okay, why is this, why does it happen, or who made it happen, and all of that. But physics is the only branch in science which describes How did it happen? How does it work? How to make it happen? How do you think this is possible, right? So if you ask that question to any occurring physical result, you will know the physics behind it. So whenever a problem is given to you regarding physics, ask yourself, how is it possible? What are the theories? What are the functions, right? So all of that we are going to study. Yes. The interplay of theory and observation or experiment is basic to the progress of science. So you see, theory and experiments are interdependent. Without theory, there's no experiment, and without experiment, there's no theory. Both are nothing, but they're very important, and science is ever dynamic. It's so dynamic in nature. There is no final theory in science and no unquestioned authority among scientists. So every scientist is questioned for his inventions, right? So if there is no question which arises, then definitely there can be no outcome of an experiment. As observations improve in detail and precision, or experiments yield to new results. So as and how the questions were asked, they went on improving in detail, checking out the details of that particular phenomena, right? So suppose if I'm telling motion, so in detail, what are the laws of motion? What are the quantities governing the motion, right? What is force? So every detail is actually being mapped, and experimentally also it is checked to have the least precision, the highest precision, right? Yes, if necessary, by introducing modifications, if the theories are modified, sometimes these modifications may not be drastic and may lie within the framework of existing theory. For example, okay, now you see here John Kepler, right, was the person who found planetary motions, correct? So before that, Nicolaus Copernicus in the year 1473 to 1543, he found something called as heliocentric theory, in which it assumed that sun is the center of the solar system. Then, by looking at Nicolaus Copernicus, Tycho Brahe collected all the data of the solar system on planetary motion. Then Johannes Kepler came. By looking at the theory of Nicolaus Copernicus and Tycho Brahe, he actually formed something called as Kepler's laws, which told that planets revolve in elliptical orbits and not in circular orbits, which led to the discard of Nicolaus Copernicus theory or heliocentric theory, which said that the sun is the center of solar system and the planets revolve in circular. So that was rejected, but it was proved that planets revolve in elliptical orbits, right? So this is something which was proven. Now we have two major quantities in physics. One is called as a macroscopic and one is called as microscopic. Macro means large quantities, right? So it may be force, it may be mass, anything that is measurable in larger quantities, that is called as macroscopic. Now microscopic is what? Micro means very small substances. Okay, so microscopic refers to substances that are large enough to be seen by the naked eyes, whereas microscopic refers to the substances that are very small, so we cannot observe them without a magnifying device. So all small substances are called as microscopic substances. Now macroscopic means large, the size is very large, but microscopic means the size is very small. Now what are the units of measurement of macroscopic particles? We can use millimeters, which are measurable, centimeters, which are measurable, kilometers, which are measurable. But microscopic particles are expressed in terms of nanometers, 10 raised to minus 9, right? Hexameters, then Armstrong units. So all these are very, very small units. Correct? So microscopic particles are measured using all these kind of scales. So, if we have to observe any microscopic phenomena, okay, any larger quantity, we do not require any magnifying glass. But if you are observing any microscopic quantity, okay, it might require magnifying optical devices such as light microscope, electron microscope, lenses and all of that. So, all that we are going to study. So there are two domains of interest called as macroscopic and microscopic. The macroscopic domain includes phenomena at the laboratory. See, everything that you use in labs, right? They are measured either in centimeters or millimeters, right? Or Yes, so all of that, milligrams, centigrams, grams, correct? So all these are measurable quantities, terrestrial and astronomical scales. That the astronomical scales are large units, right? So all these come under something called as classical physics. Classical physics is nothing but a branch in physics which deals with macroscopic particles. Now what does microscopic domain include? Microscopic domain mainly includes atomic, molecular and nuclear. Okay, atoms which are very minute, which are very small. Okay, the precision is very small. The microscopic domain of physics deals with the constitution and structure of matter, that the minute scales of atoms and nuclei, even lower scales of length, and their interaction with different probes such as electrons, protons and other elementary particles. Elementary particles means antimatter and all of that, that you will study in your later classes. Yes. So the macroscopic domain, you have something called as classical physics. So what is the components that classical physics include? It includes mechanics. Mechanics means laws of motion, right? All the force, pressure, everything comes under mechanics. Everything that is physical, right? Physically possible comes under mechanics. Then you have thermodynamics and kinetic theory of gases, heat and all of that, right, comes under thermodynamics. Optics, lens, light, all of that. Electricity and magnetism, acoustics, sound comes under it. Astrophysics comes under it, and relativity comes under it. Then in mechanics you have statistics and dynamics, and in dynamics you have kinematics and kinetics. So all these are nothing but different branches in classical physics. Okay children. Yes. Now let me tell you a bit history about physics. Okay, so what happened, how these scientists played an important role in different discoveries, and why is it so exciting, what is the scope of physics, right, what happened basically, and all of that. Little bit history class we will have today in physics. Okay, so you all know what is Newtonian mechanics, right? You all have studied Newton's laws of motion, right? A body continues to be in the state of rest until and unless an external force acts upon it. Inertia, right? Then action and reaction, all that forces you, force is equal to mass into acceleration, right? All that you have studied. So Newtonian mechanics is based on the application of Newton's laws of motion, which assumes that concepts of distance, time and mass are absolute, that is motion is in an inertial frame. Okay, so we assume that motion is in inertial frame in Newtonian mechanics. But what does atomic theory include? See, Newtonian mechanics is a macroscopic quantity. Okay, atomic theory is a microscopic quantity. So atomic physics is a field of physics that studies atoms as an isolated system of electrons and an atomic nucleus. It is primarily concerned with the arrangement of electrons around the nucleus and the processes by which these arrangements change. Oh, okay. So basically atomic theory is everything about atoms. It is an isolated system. Atom is separate, right? It is isolated. Then it is concerned with the arrangement of electrons, how the electrons are arranged, right? So if I am applying Newtonian mechanics to atomic theory, do you think it's applicable? Right? So you see here Newton's laws, which was so successful in allowing us to understand the behavior of big objects. So we used to say, the body continues to be in the state of rest until and unless an external force acts upon it. Right? Now, what happens in atomic theory? If a force is applied on atomic theory, in atoms basically, okay, so if I'm applying Newtonian mechanics to atomic theory, okay, so Newton's laws, which were so successful in allowing us to understand the behavior of big objects such as the motions of planets, okay, failed when pushed to explain atomic size phenomena. Very quickly what happens is, whenever a force comes into a picture of an atom, very quickly the electron would lose all of its energy and there would be no atoms. Instead, when electron falls down to a lower orbit, a photon is emitted. Right, so the Newtonian mechanics fails to explain atomic theory. Right, now similarly, wave picture of light. Now we know that wave, right, the light travels in the form of waves. We know that wave speed is there, you know the amplitude, how high it is, how low it is, right? You know what is wavelength, the difference between two crusts and troughs. So in a wave picture of light, intensity of the light is determined by the square of the amplitude. So intensity, how bright is the light, depends on how much big is the amplitude. Square of the amplitude we assume. But what is does wave theory explain photoelectric effect? The photoelectric effect means the emission of electrons when electromagnetic radiation such as light hits a material, right? So it says that a photoelectric effect is only possible, it is the emission of electrons, they say, when electromagnetic radiation such as light hits a material. So that is nothing but photoelectric effect. So here they say the intensity is determined by square of the amplitude. So just wave is enough, they say. But photoelectric effect says that until and unless the emissions are, it's nothing, electrons are emitted. Okay, the electrons are emitted when electromagnetic radiation such as light hits the material, they say. So this wave picture fails to explain photoelectric effect. The wave nature of light fails to explain because when the waves of light of higher intensity fall on the metal surfaces, more energy will be imparted to the electrons. Hence the kinetic energy of the ejected electrons will become more. Right? So here is where the wave picture fails to explain photoelectric effect. Photoelectric effect. So, occasionally, however, the existing theory is simply unable to explain new observations. This causes a major upheaval in science. They were like, why are these theories, why is classical mechanics not able to provide enough evidence for smaller matters, right, for small substances? In the beginning of 20th century, it was realized that Newtonian mechanics still then was a successful theory. Nobody could prove it is wrong. Okay, only until and unless it could explain some atomic phenomena. Similarly, then the accepted wave picture came, and that also failed to explain photoelectric effect. This led to the development of a radically new theory called as quantum mechanics to deal with atomic and molecular phenomena. Alright, so quantum mechanics came into picture there. Quantum physics, we call it. So quantum physics has various branches like quantum optics, nuclear physics, atoms and molecules, subatomic particles, right? So all these micro particles are dealt in quantum physics. Macro particles are dealt in classical physics and thermodynamics and all of that. But microscopic particles, very smaller size particles, are nothing but dealt in quantum physics, right? So now let us go little bit ahead in quantum physics. Now we all know Ernest Rutherford, right? So what did Ernest Rutherford do? He showed that scattering of alpha particles by gold foil, right? So what he said, now suppose this is an arrangement, okay, there's a microscope, there's fluorescent screen, okay, then there's gold foil, this is polonium sample, and there's black block. Now, a small number of alpha particles were deflected by large angles, that is greater than 4 degrees, as they passed through the foil. A very small number of alpha particles came straight back off the foil. Hence, this experiment led to the discovery of atomic nucleus. So, theory and experiment go hand in hand in physics, and they help each other's progress. The alpha scattering experiments of Rutherford gave the nuclear model of the atom. So, looking at this, so why does it happen that way, right? So, why a small number of alpha particles, they were deflected by large angles in the scattering of alpha particles by gold foil experiment. So, very small number of alpha particles came straight back off the foil, right? So, why is it? That was nothing but it led to a great discovery in physics. I'll tell you what it is. So, before that, this is basically how this, scattering of alpha particle looks like. Okay, so you see, this is a microscope. So, what happens is we leave a beam of alpha particles, right? So, there is a lead shield. So, alpha particles beam we leave. Now, they go and pass through a lead screen with a slit, and they go to the gold foil. Now at A, at the screen, fluorescent screen, there are all fluorescent screens there. Okay, so at A there is a little, there's a little scattering, transmitted beam, whatever it is, there's little or no deflection at all. But for B and C there are huge deflections of the scattered beam, right? So why is that? That is nothing but what? The scattering of alpha particles, that is more than 4 degrees, which led to a new theory in quantum theory, that is called as the hydrogen atom, right? So that is where Bohr discovered a new Bohr's atomic model came into existence, right? So Niels Bohr in 1885 to 1962 shows that atom has as a very small positively charged nucleus surrounded by orbiting electrons. So there's an atom here, okay? So he proposed a model called as Bohr's atomic model. He showed how an atom looks like, what is there in the atoms, why are they deflected in a larger angle, right? So because of the alpha scattering, it led to the quantum theory of hydrogen. It was, all the constituent particles of the atom, the protons, electrons, neutrons, okay, they were completely explained by Niels Bohr. So we call it as atomic model. Right? So protons and neutrons are found in the nucleus, he said. Electrons are orbiting around the nucleus in various shells, right? So everything else is the empty space. So the Bohr's model shows that the atom has a very small positively charged nucleus. So atom is a very small and it is positively charged nucleus surrounded by all the orbiting electrons, he said. Then Bohr was the first to discover that electrons travel in separate orbits around the nucleus and that the number of electrons in the outer orbit determines the properties of an element, right? So why did the alpha particles scatter that way? Because of the electrons that are present, right? The outer orbit determines the properties of an element, how it deflects, what it does. Understood, children? So these all theory one by one were discovered. So as a new experiment may suggest an alternative theoretical model, a theoretical advance may suggest what to look for in some experiments. Now as we saw, the result of experiment of scattering of alpha particles by gold foil, which was in 1911 by Ernest Rutherford, established the nuclear model. Because of alpha particle scattering, we came to know the nuclear model of atom. That was the basis for quantum theory of hydrogen atom given by Niels Bohr, right? Because we know what the nuclear model of atom looks like, that's when this hydrogen atom came into picture. On the other hand, the concept of antiparticle was introduced theoretically by Paul Dirac. Paul Dirac is also one of the scientists who introduced something called as antiparticle in quantum physics, or and confirmed 2 years later by the experimental discovery of positron, that is anti-electron, by Carl Anderson. Now you see here, and Paul Dirac found something called as antiparticle. Now what is this antiparticle? We have particles like electron, proton and neutrino. Right? Now the opposite of particle is antiparticle. More about this you'll study in your higher classes. Okay, so antiparticle is nothing but opposite of all the particles. Now electron is nothing but, electron will become positron. Okay, so positron are anti-electron. So that is an antiparticle, opposite of particle. Understood? Proton will become anti-proton. Neutrino will become anti-neutrino. Right? So what are these antiparticles? It is a subatomic particle. In an atom, it is a subatom. Okay, so in a subatomic particle having the same mass, see, they have same mass. Okay, what is the mass of electron? Same is the mass of positron. What is the mass of proton? Same is the mass of antiproton. What is the mass of neutrino? Same is the mass of antineutrino. Okay, at a given particle, but opposite electric or magnetic properties they have. What kind of properties? They have opposite electric or magnetic properties. All opposite properties they have. Okay, if electron is negatively charged particle, positron is anti-electron, same mass as that of electron, but it has a positive charge. A positive electron, we call it, is called as a positron. right? So every kind of subatomic particle has a corresponding antiparticle. Example, the positron has the same mass as the electron but an equal and opposite charge. So antiparticle was found by Paul Dirac. Now the positron was discovered by Carl Anderson by studying the tracks of cosmic ray particles in the cloud chamber. Okay, so he studied all these cosmic ray particles in this cloud and he discovered a positively charged particle with a mass seeming equal to that of an electron. So Carl Anderson's particle was the first antiparticle proven by experiment. He experimented on what theory the Paul Dirac had produced, right? He assumed and he produced, but it was proven right. It was proven right by Carl Anderson, right? So all these scientists have played a very big role in physics. Now, always remember there are two basic quests or domains in physics, that is unification and reductionism. Okay, now what is this unification? Entire physics deals with unification and reductionism. Now unification is nothing but it is an attempt to explain various physical phenomena in terms of just few concepts and laws. Example, the same law of gravitation can be used to describe the motion of freely falling body and motion of planets around the earth. We unify them, right? So various physical phenomena in just few concepts we use and we unify all the theory. We bring it together. It's universal, right? So that is called as unification. Next is reductionism. Now what is this reductionism? It explains a macroscopic system in terms of microscopic constituents. Like thermodynamics explains the macroscopic properties like temperature, internal energy, entropy and all, right? But kinetic theory explains what? These same properties it explains like temperature, internal energy, entropy, in these properties in terms of molecules. Understood? One explains the macroscopic properties, thermodynamics, and kinetic theory, same thing it explains in terms of molecules. Understood? So that is called as reductionism. Same concept we apply, okay, and it is used for the similar theory and very simple theories. That is called as reductionism. Yes. Now there's huge scope and excitement in physics. There are various branches in physics, right? So you have something called as mechanics, which deals with motion and causes. We have optics, which deals with the behavior of light. Thermodynamics, which deals with heat and temperature. We have vibrations and waves, which deals with periodic motion. We have atomic structure of the atom, okay? Energy associated with atomic charges. Then we have nuclear physics, which deals with structure of nucleus, energy associated with all the nuclear charges. Then we have electromagnetism, right, which deals with electricity, magnetism and waves. So there are huge scope there are various branches and each branch has huge scope in the terms of physical world. Yes, so basically we have classical physics, which deals with motion, gravitation, calculus, optics, mechanics, waves, fluid mechanics, electromagnetism, right? Thermodynamics, everything comes under classical physics. Then we have relativity, theory of relativity, right? So speed of light comes into picture, special theory of relativity, quantum field theory, atomic theory, okay, condensed matter physics, particle physics. So all that particle and antiparticle, what I taught you, comes under what? Particle physics. Then you have nuclear physics. Then you also have so many things, right? Then future they may also come up with quantum gravity, then Park's energy, dark matter. Today even dark matter's theory is hugely in scope. Today every scientist is focused on dark matter physics. Then you see there is free will. There is free will to ask how come, okay, what is the reality of the nature, just why. So all these are nothing but physics is a very exciting subject. It is a very curious subject to know why does this happen, why does this happen, or why does that happen, how does it do it, right, how it happens, what is the physical phenomena behind it. So there's a huge excitement and scope of physics. right? And we all know what are the basic laws in physics, right? So laws of motion, Ohm's law, Avogadro's law, conservation of energy, angular momentum, laws of friction, laws of gravitation, Archimedes principle. Then we have basic theories in physics like classical mechanics, relativistic mechanics, quantum theory, classical electromagnetism. So all this you will study, children, okay? So there are basic theories and basic laws. So you can only make a law successful until and unless theory and explains why the phenomena occurs, and scientific law which describes what phenomena happen, okay? Together, if we combine them, then you will have repeated successful predictions. So how do you predict a theory? How do you predict an experiment? If only you merge the theory with the law. Laws are nothing but universally proven, right? They are fundamental in nature. They are very universally proven and tried out by various people. That's when you get a scientific law. So if this law tallies with scientific theory, then you will get successful predictions in physics. Yes, so physics is really exciting. How? Physics is exciting in many ways. To some people, the excitement becomes from the elegance and universality of its basic theories, from the fact that few basic concepts and laws can explain phenomena covering a large number of magnitude of physical quantities. Physical quantities like mass, time, energy, space, time, right? All these are physical quantities. Length, mass and time. Now, to some others, the challenge in carrying out imaginative new experiments to unlock the secrets of nature. Some people want to unlock new secrets of nature, right? So what do? To check out the future future theories is really thrilling, right? So they take up that challenge. That is when physics becomes really exciting, to unlock new secrets of nature. What happens? What is the future, right? All this they do. Then applied physics is equally demanding. Application of physics, right? So application and exploitation of physical laws to make useful devices is the most interesting and exciting part, and requires great ingenuity and persistence of effect. Now see, today's day robots are come into picture. Robotics is a huge branch in science, right? In engineering, you may say. Then even artificial intelligence, there's data science, all these things, right? We apply all these laws, how to function it, how do we do it, what is the theory behind it, right? We use all these physical law and we also make useful devices. Yes, so there's been a phenomenal progress in physics in last few centuries. First, it was realized that for scientific progress, only some thinking is enough. But that thinking was just not enough until and unless some mathematical equations came into picture. That means not just the quality is enough, but also the quantity is also equally responsible. There should be some quantity to support it. There should be some theory. There should be some calculation. There should be some evidence. Not just thinking that this might happen, but also proving that this is the possible one. Right? So the second most important insight was the basic laws of physics are universal. All these physical laws of motion, Kepler's laws, then friction laws, conservation laws, all Ohm's law, magnetism, whatever laws that we study are universal. Till date, they cannot be proven wrong. But in case if they are proven, then some other theories which are right and experimented, they can also be applied. Lastly, the strategy of approximation. See, whenever we prove an experiment, it should be approximated, right? Approximation is very successful because the approximation came into picture. People started, okay, this experiment happened, but how much is it efficient? Efficiency came ahead with approximation, right? Yes. Then scientists recognize the importance of extracting the essential features of a phenomena from its less significant aspects. It is not practical to take into account all the complexities of a phenomena in one go. A good strategy is required to focus first on the essential features. First, we need to have good strategy. How do I do it? Like example, A stone and a feather dropped from the same height do not reach the ground at the same time. Stone will reach soon, feather will reach little late. The reason is that essential aspect of the phenomena, namely free fall, both are having gravity, both are falling because earth is having gravity, that's why they fall underground. But that is when air resistance also comes into picture. There is a resistance of air which actually makes feather to come little low, right? So you see 2-3 concepts are linked together. Correct? So to get the law of free fall under gravity, it is better to create a situation wherein the air resistance is negligible. So once we put air resistance negligible, then only we can say, okay, this is a free fall under gravity. Right? So example, let the stone and feather fall through a long evacuated tube. In that case, the two objects will fall almost the same rate, giving the basic law that acceleration due to gravity is independent of the mass of the object. So that is when they say that acceleration with whatever it is falling, it is independent. Right? Though mass is different, the acceleration is equal to that, rate of falling of that object. So with the basic law this found, we can go back to the feather, introduce corrections due to air resistance, modify the existing theory and try to build a more realistic theory. So this was just an approach. Okay. So what did I do here? I applied a scientific method. First one example I took, right? Then I reasoned what can it be, what I can do it. Then I tested with a hypothesis, right? All that I have done to get a final theory, and that is called as a scientific method. So what is scientific method we will learn. Okay, so before we go ahead with knowing what is the scientific method, first thing we need to know are the two most important things here. One is called as the hypothesis and the next thing is called as axioms and models. Okay, now what is this hypothesis? Hypothesis means it is a suggested solution for an unexplained occurrence that does not fit into current accepted scientific theory. The basic idea of a hypothesis is that there is no predetermined outcome. It is just a thinking, okay? It is just a prediction. We still don't know if it can be true. Okay, we have just assumed it by knowing all the previous knowledge about that particular thing. Okay, now in simple words, a hypothesis is an educated guess about something in the world around you. It should be testable either by experiment or observations, right? So see, even Niels Bohr, even all of the people, even Newton's laws, right? Everybody, all these scientists assumed certain things before they proved that law. Okay, let us assume that gravity exists. So what are the things that are governing it? So that's a hypothesis. We still don't know if it actually exists, right? I'm just assuming by knowing all the previous knowledge about that particular concept. That is called as hypothesis. Okay, it is a suggested solution but not an actual solution, just to fit into that current scenario. All right, next. For example, the universal law of gravitation proposed by Newton is an assumption or hypothesis which he proposed out of his ingenuity. Before him, there were several observations, experiments and data on the motion of planets around the sun, motion of moon around the earth, pendulums, bodies falling towards the earth. So all this was actually proven that time. There were a lot of evidences. Okay, before Newton's law of gravitation came into picture, there were very previous theories. So each of these required a separate explanation which was more or less qualitative. Okay, qualitative means still there was no mathematical formula there. It was just an intelligence aspect, right? Just the thinking process was there. So, okay, which was less qualitative. Now, what is the universal law of gravitation say is that if we assume that any two bodies, okay, suppose there are two bodies, like suppose one mass of one sun and planet if we take, right? If there are two masses, okay, they attract each other with a force that is proportional to the product of their masses. If the sun's mass is m1 and the planet's mass is m2, so the force between them is nothing but product of their masses, and it is inversely proportional. That means divided by the square of the distance between them. If the distance between the sun and the planet is 5 million something, okay, kilometers, then it's the square of it, right, in astronomical units. Then we explain this phenomena in all one stroke. It only explains these phenomena. It also allows us to predict the results of the future experiments. So by looking at this, by studying all the theory behind it, assuming things, we can prove a theory forward. So a hypothesis is supposition without assuming that it is true. It is just a supposition. Suppose this happens. Suppose that happens. We still don't know if it is true. Okay, that is called hypothesis. It's just an assumption. Understood? But assumption with facts. Understood? Yes. So it would not be fair to ask anybody to prove the universal law of gravitation because it cannot be proved. It can be verified and substantiated by experiments and observations, right? So we already know that gravitation force is not directly proportional to product of the masses and inversely proportional to the square of the distance between the objects, right? So this is called as the universal law of gravitation. Right? And how did Newton prove it? Only by assuming the previous knowledge, by getting all the knowledge previously, by putting it in terms of, all that. Now, next is axioms. Axiom is nothing but a fact. It's a self-evident truth. Right? So an axiom is a self-evident truth, while a model is a theory proposed to explain the observed phenomenon. So hypothesis is there, axiom, we know the facts, and we need a model to express it. Correct? So hypothesis, axioms and models come in one go. Example, next year you will learn about Bohr's model of hydrogen atom, in which Bohr assumed that electron in hydrogen atom follows certain rules or postulates. So see, even that electron has certain rules. Okay, so Bohr, before proving his theory, Bohr's atomic theory, before that came into existence, he had assumed certain postulates in his mind, right? So why did he do that? There was a large amount of spectroscopic data available before him. So in spectrum, there was a large data available. Using that, he found his theory. Right? So Bohr said that if we assume that an atom behaves in such a manner, we can explain all these things at once, right? So even Einstein's theory of relativity is based on these two postulates, that the constancy of speed of electromagnetic radiation and validity of physical laws in all the inertial frames of reference. So it's a self-evident truth. I don't have to explain anybody that it is true. It is already proven truth. It's a fact, right? So that is called as axiom, and the model is required to prove it. Right? So, but now knowing what a hypothesis and doing a background research about it, now we know what are facts, right? Now we have to create a model. So this entire process is called a scientific method. Okay? So what is scientific method? First thing is, a question is asked to you, right? A systematic observation. First step is a systematic observation. What comes under systematic observation? One question is asked to you. Okay, you do background research. What are the facts concerning it? What is this? What is that? You reason. Correct? Reason means you will construct one hypothesis. Now I have done research. Okay, I will do some hypothesis. I will put some hypothesis. If this, let us assume that. Okay, so things is there. Alright, so let us assume that this happens. So that hypothesis I have to test. Correct? So to test the hypothesis with an experiment, that's when the mathematical modeling comes into picture, right? With all the mathematical equations, whatever formulas I know, I will test it. And I will check if the procedure is working or not. If it is working, then I will analyze the data and draw conclusion, that is theoretical predictions, right? If the procedure is not working, then what is the thing that is, I have to troubleshoot it, right? So what is the thing that is troubling me not to get the result? Again, I do the retesting with an experiment, right? Then I analyze and get the conclusion, and once I get the conclusion, then therefore we prove that the hypothesis is true. Once the hypothesis becomes true, then we communicate the result, and that's how a theory is proved. That's where a theoretical prediction comes into picture. So first thing is what in scientific method? Systematic observation, where a question is asked and a background research is done. Then we will reason. To reason, we have to construct a hypothesis. Let us assume that so. Then we test it with certain experiment. Then is this procedure working? Right? So mathematical model comes into picture. Yes, then analyze and draw conclusion. Prove that the theory is right. If no, then what is the error that has happened? Correct? So this entire procedure of deriving a theory using all the laws is called a scientific method. Physics is so exciting, children. Yes, so here we have come to the conclusion of this class. So in this class we have studied what is science, it means to know. What is physics? It's a way of describing the physical world, which means nature. Then what are the various branches of physics? What is the scope of physics? What do you mean by unification and reductionism? What is the progress and excitement in physics? What are hypotheses and axioms? In the next class we are going to study the forces that govern nature. Right, so forces and different kinds of forces in nature, and about all of scientists, all that we are going to study in the next class. I hope you understood till here. Thank you and have a nice day. See you in the next class.